We are continuing in Unit 6 of our OER Statistics course, where we are discussing the central limit theorem. And in Unit 6.2, we will discuss the central limit theorem for sums. And in the Introductory Statistics by OpenStax book, this is section 7.2. And in the Lumen Intro Statistics Corequisite book, this is again in module 7, the central limit theorem for sums. And an example of where we would want to use sums is, for example, when an elevator requires a maximum capacity of 2,000 pounds, and we want to know if 10 people, 10 adults, will have an average total weight of 2,000 pounds or more. So the central limit theorem for sums has some similar application and allows us to answer questions like this one. So suppose we have a random variable x with some distribution and a mean of mu sub x and a standard deviation of sigma sub x. The central limit theorem for sums states that if you draw random samples of size n, as n increases, the random variable sum of x values tends to be normally distributed. And the distribution will have a mean of n times the mean of the variable and a standard deviation of square root of n times the standard deviation of your variable. So the standard error will be the standard deviation times the square root of n. The z-score for your random variable sum of x will be the sum of the values that you ended up from your sample minus the mean of the distribution of the sums, which is n times the mean of x, divided by the standard error of the sums, which is the sigma of x times the square root of n. And to do an example pertaining to this, we have the mean number of minutes for app engagement by a tablet user to be 8.2 minutes, and the standard deviation to be 1 minute, and we take a sample of size 70. So we have the mean of our variable to be 8.2, the standard deviation of our variable to be 1, and the sample size to be 70, and we are trying to find the sum distribution. Since the sample size is 70, which is greater than 30, the central limit theorem indicates that the distribution of the sums will be normally distributed, and that will be the total length of time of app engagement for 70 people measured in minutes. I will want to know something like that. For example, if I had an internet cafe and I will want to know the total amount of engagement, the total times. So there are many cases where I would want to know the total sum. So the mean for that, for this distribution, will be the mu of the sum of x will be n times the mu of x, 8.2, and 70 times 8.2 is 574 minutes. So this value in the middle here will be 574. The standard deviation of the sums will be the standard deviation that I have times the square root of 70. And the square root of 70 is approximately, let's find out. It's a little less than 9 and more than 8. So let's find out in our calculator what is the square root of 70. And the answer is 8.3666. So approximately 8.3666 minutes. So every tick mark here for the sums will be approximately 8.3666 minutes. So let's go in Art of Stat and change our mean to 574 and change our standard deviation to 8.3666. And ideally you want to do more, but for now we will save some time. And let's answer the question. Actually, let me just copy these values. So I have 582.367, 590.73, etc., etc. So let me do that. So 582.4, 590.7, 599.1, and going down I have 565.6, 557.3, etc. to the left. What's the probability that the sum of the sample is between 7 and 10 hours? So the question is, what's the probability 7 less than the sum of x less than 10? And 7 hours is 7 times 60 minutes, which is 420 minutes. 420 minutes is really, really low here, 420. And 10 hours will be 600 minutes, and 600 minutes is also up here. And it will, I'm expecting to see something equal to 1 to 100%. So let's find out. So in this app, I want the probability on an interval. I want the interval to be 420 minutes. And I want the upper bound to be 600 minutes. And this says that the probability is 0.9991. And the next question is to find the 84th and 16th percentiles for the sum of the sample and interpret these values in context. So I am expecting that these values will be very close to the empirical rule. We have done the empirical rule several times, and we have seen these values. We know that the middle is the mean is also the median, so it splits the distribution into 50% and 50% above and below the mean. But the first standard deviation gives us the middle 68% of the data, which gives us 34% below the mean and above one standard deviation below the mean, and 34% above the mean and one standard deviation above the mean, which is 582.4, and this is 565.6. And we know that below that value, I will have 16% of the data. And then from 34% above the mean all the way to the left, that will be an 84% of the data. So I'm expecting that the 84th and the 16th percentiles will be very close to these values that are one standard deviation away from the mean. So let's see if that is true from our app. So I'm going to go under find percentile quantile. I'm going to look for the lower tail. I need the 16th percentile. And the 16th percentile comes out to be 565.68. Mathematically, The probability that the sum of the x values will be less than 565.68 is 0.16. And in English, 16% of the total time, the sum of the times spent for app engagement by tablet users, by 70 tablet users, is expected to be 565.68 or less, the 16% of the time. And then for the 84th percentile, I'm expecting again to be very close to 582.4. So let's try that. So if I want this to be 84% of the time, I am at 582.32. So the probability that the sum of the app engagement times for the 70 users being less than 582.3 is 0.84. And again, 84% of the times, we expect the total time that 70 tablet users will spend on app engagement will be 582.3 minutes or less. Remember the glossary for us for this section? We did the central limit theorem for the sums that indicates that if we have sufficiently large samples greater than or equal to 30 in sample size, then the variable of the sum of x will be normally distributed with a mean of n times mu and a standard deviation of sigma times the square root of n, regardless of the shape of the data. The distribution of the data.